Hey, Mr. Shrek. You kind of lost me at the last lecture. Now, I am starting to, or after going over the guided notes and after checking through the slides again, I'm starting to understand. I'm starting to recognize a couple of patterns associated with uh, integration. Um,
Good.
but I'm not entirely clear on the story. So let me see if I can find any
So
specific.
Catherine, you and I were talking integration before in the story. So if you're within earshot, you might want to listen in because I'm going to go through it also with Doug.
Yeah, okay.
Okay, so just as a heads up. So go ahead, Doug.
Okay.
So tell me what you feel good on it with the story. Tell me what's gotten confusing.
So I am understanding that it is, it's still we're still working on the Riemann sum idea, just mapping the curve or mapping the area between the x-axis and the curve with infinite number of rectangles.
That's
So
the idea.
that
So remember, like, yeah, we've got platforms of models and stories we've done so far, and so like, yeah, that was a very good summary. So just to capture that, so remember,
Yep.
we started off with this idea of like, how do I handle forever?
Yep.
And we said I can kind of get close to that if I consider a big list of numbers. We call that the method of exhaustion.
Yeah.
And that we said, okay, but if I can find a strategy or an expression,
Mm-hmm.
then I can run that through limits.
Yep.
And that is the actual thing that gets me to perfect.
Yep.
So like we've got all this stuff happening behind the scenes underneath it. And so you did a great capturing. If I want to find perfect area, I need to make a list. How do I make the list? I consider the Riemann sums as they're becoming more and more accurate. That
Yeah.
helps me capture the perfect forever.
Okay. However, and I'm understanding the concepts of acceleration, velocity, and um, what is it? The distance traveled.
Displacement. Yep.
Yeah, displacement. I'm understanding that. I'm understanding summations. However, so it is. I don't know. Let me try to.
Yeah, I can see. Yeah.
Okay. It is moving from this expression to this and then getting a final answer out of it. I understand this is, the sum of starting point and ending point. And then we've
Good.
got
What are
the
those? List those
function.
numbers off for me.
Yeah. The sum from 0 to 10.
Good.
And I understand this is the, f of x, the function of x.
Which one was that say?
X to the 20th. And this is the, the change measured in x, or the delta x. So
Yeah, good. So don't look at these as a thing that I'm going to try to compute directly.
yeah.
This isn't algebra. The difference between this notation is that like this notation is not here's the problem, go do the problem. We
Okay.
first need to bring it back for its meaning, which
Okay.
we've actually done. So as a parallel, think way back to like third grade. In third grade, if we were trying to learn what is 5 times 4, we didn't know this. This wasn't a thing we even understood.
Yep.
The first way we were taught about this is we had to break it down to 5 plus 5 plus 5 plus 5.
Yep.
Then we recognized what it meant. Then I could do it. And through practice of understanding this is 20, we eventually got to a place of comfort where we said, oh, this is just a thing I do.
Yep.
But this was never the how I did it.
Yep.
Right? So we're going to do the same thing here. It's asking us to do a story 5 times of 4. How do I do the 5 times of 4? I might need to reach for other representations, other tools to make that story something I can get.
Yes.
Okay, so we can't always punch the notation directly. The notation is just telling us what we want to conclude with. What we want
Okay.
at the very end of all this is we want, exactly as you said it, the perfect area from 0 to 10
Yep.
across using f of x equals x to the 20th and forever small rectangles.
Okay.
So that's just what I want. That's not the how. That's just the end destination. That's the goalpost.
Okay.
Okay. Now, how do we do that? Any way we want. Now, the ways that we've come to think about strategies is we could try it with some rectangles, right? We could do this as a Riemann sum. That's an idea. We could run this via Riemann sum. That would be great. It's challenging and difficult, especially when we're trying to do it to the 20th power. The amount of foiling and factoring and distributing would be absurd.
Yeah.
But it would work and it would be true. So that's one way we could do it. We just immediately hit roadblock. All right,
Yep.
so we're going to go for a different method of approach. The method of approach that we introduced last class is that we have a power pattern. A power pattern is a way of doing the Riemann sum thought. We're just going to do it really, really quickly through the pattern.
Yeah.
Okay, so we're going to do the power pattern, what they sometimes call the power rule. So power pattern. All right, what's the power pattern say?
That's beyond my well, the pattern that I've concluded is that it's going to be a lot similar to, well, it's not going to be a lot similar. It's going to be kind of similar to the summation for squares.
Sure.
Except
So remember, summation just means I want to do a bunch of addition. Do we want to do a bunch of addition here?
No.
Because that's going to be exhausting, right? Like, could we do it? Right thought process? Yes.
Yeah.
Actually doing summations, tough.
Yeah, and time consuming too. You're not going to give us 3 days for the test.
Right,
So,
right. So
Uh,
after we looked at a few of the case examples of doing these Riemann sums, right? Because we did a Riemann sum for constants. If it's just a graph going straight across, that would just be very simple rectangles.
Yep.
That's easy. Triangles, we don't have to even do the rectangles in it. We just know it's going to form a triangle.
Yeah.
So the rectangles will become a triangle, and we can just do triangles. So we'll just kind of circumnavigate that problem. So we've got constants where I did the integral of a constant from a to b dx. That came out as that height times the width. The width was whatever's between a and b. All right, b minus a. There you go. So it was essentially bring this into a structure of c times x, and then plug in b for that x, and then subtract it from a of that x. So I guess I could write it like this. C times b minus c times a, right? Gets me the same rectangle.
Yep.
Okay, so we've got a structure here. If I have no x's, I can use an expression that has x to the first power. Got it. If I have 1x, then that makes it linear. Linear goes along with triangles. Triangles, when we ran that one through, we ended up getting that had the structure of c times x squared divided by 2. because
Yep.
that came from the idea of 1/2 base times height, where my base was x and my height depended on x. So I got that structure, which was c divided by 2 plug in b squared minus c divided by 2 plug in a squared, right?
Yep.
And then we also exposed it for what about when I did it with the quadratic? That became a 1/3 x to the third. And then if it was integral of x to the third, it became x to the 4th over 4.
Mhm.
We had a power pattern that we began to recognize. So let's look at that power pattern here. If I imagine doing the Riemann sum, so I'm still holding the logic true, I'm just imagining doing it faster than I could actually do it.
Yeah.
What is that 20 going to turn into?
It's eventually going to turn into a 21.
It's going to turn into a 21. And then I'm going to divide by
21 as well.
21. And again, if you want to verify that with the Riemann sum, you can. It's going to be long and exhausting, and there's a better
Yeah.
proof general form in the guided notes that just says, like, this is actually like not just a pattern, this is a has to be. So we've got, we can take advantage of it as a way of holding true to the Riemann sum, but not doing it directly, in the same way as this is holding true to the repeated addition. I'm just not doing it directly, right?
Okay.
So once we have this, now I need to plug it in. That's the structure. I need to use that structure with 10 and 0. So let's do it with 10. That'd be 10 to the 21st over 21. Minus plug in 0, that'd be a 0 to the 21st over 21. This all goes away. I'm left with my final answer.
So where I'm kind of separating from you is, so let's look at the bottom example you got there, the sum of a to b, the function being cx, cx.
So do me a favor and start reading this as integral, because sum means I'm going to do some addition. Integral means I already did it.
Sure.
Right? I'm already at perfect. However I got there, doesn't matter. It's not telling me the how, it's just telling me the what I want to have at the end.
Mm-hmm.
Okay, so go ahead.
So the integral between a and b function, or the integral between a and b of c of x.
Just c.
How would, yeah.
Just c dx. So graphically, that means it's just a constant function wherever c is. If c is there, that's my graph.
The other one would be a slope line, or a sloped line, and then the one immediately following that would be a curved quadratic. But so what I'm not understanding, I suppose, is how out of a power of 20 on the function do we get 21?
Because so it all comes back down to what's the power pattern from. The power pattern came about as us looking at a few examples of Riemann sums and going, I think there's a pattern.
Yep.
Then through the guided notes material, we're able to prove, oh my God, there is a pattern.
Okay.
Always.
Mm-hmm.
So now I don't have to go through the process of make a bunch of rectangles, express a bunch of rectangles, run those rectangles skinny.
Yeah.
I can just be like, that's always going to result in the pattern.
Mm-hmm.
Like, it came from the rectangles, but I don't have to do the rectangles anymore because the rectangles will always result in this pattern. Let's just do the pattern.
Okay.
So this is coming about from the fact of, I want to do Riemann sums, but why do Riemann sums directly if I know the Riemann sums will always follow this pattern? Let's just do the pattern. It's the same thing.
Okay.
Okay. So, and again, how do we know that to be true? I've given you a couple of case examples. After you hit x to the 4th, running the Riemann sum directly becomes very, very hard certainly impossible for x to the 20th, at least with the time that I have to spare. And so it's a matter of like, okay, how did we prove that this will work all the time? That's where the proof in the guided notes walks people through that and kind of proves that one legitimately. But for our purposes, we're just going to go with like, hey, there is a proof. This pattern is what the Riemann sum exposes. So anytime we want to do a Riemann sum and it's the structure we're talking about, let's just pretend we did the Riemann sum because it would have resulted in the power pattern.
Okay.
In the same way as if I say, what is 3 times 100, you're not actually going through this adding 100 threes.
Yeah.
You're saying, I understand that just would have been 3 groupings of 100, so I'll just call it 300. Like you're circumnavigating the storyline because you've already found a shortcut that holds true to the meaning.
Understood. Okay. Oh, that's that. So let me, because we're not always going to get integrals of just simple x to the nth power, right? You know, are there, you know, integrals of other, you know, other quadratic or other, you know, whatever equations?
I love the
Or,
questions you
no,
ask.
am I
You ask
gonna
such good
regret asking
questions.
that? Yeah.
You ask such good questions. See, well, before I go on from here, Catherine, you were working on a problem like this. Are we kind of feeling better on the story now? I don't know if you're listening in on that or not.
So I'm confused about the CX, the DX, where the X comes from with that CX
This right here?
on the bottom.
Yeah, so that's, again, I can't stress enough that this has to be read as a story because it's not the what our eyes see is not always exactly what we're trying to say, right? And that happens in math all the time. Like, for example, what do parentheses mean? Well, if I write it like this, it means multiplication. If I write it like this, it means a function. If I write it like this, then it would be an interval. Like it means parentheses don't always mean the same thing. We don't let the parentheses drive us. We let what the parentheses mean drive us, right?
Mm-hmm.
So the same thing's true over here. What's this talking about? This is talking about forever skinny rectangles. What's this talking about? This is talking about a height that I use against my function. What does this mean? This means I want to talk about the perfect addition of those forever skinny rectangles across a domain. So it's all the story that we're just trying to condense and make smaller. So what does dx mean? Dx means forever skinny changes along my sideways, right?
So DX is the forever skinny of the rectangle, and then
Yes.
the X.
Ready? So here's an example of that. Also, here's a parallel to help you out. What does this mean?
The change of the rate of change.
So you've already got, like, you've already seen this in math before, where like symbol. If I said, well, what do I plug in for delta? You'd be like, that's not at all what it means, right?
Mm-hmm.
Like I don't plug in for delta and I don't plug in for y. This is talking about a story. This says, what's my change in y? Like that's a story. I got to go exploring the story. I got to start doing math that supports the story, not math that I plug into the symbols. So yeah, what does dx mean? Dx means forever skinny rectangles. What do we plug in for dx? That's not the story that we're playing with because I can't plug in anything that would represent forever small. There's no number that works for that. Right? Unless you want to plug in 0, but then a whole bunch of zeros doesn't work either. Like we have to approach this through our class exploration.
Okay, so then what's the meaning?
Does that clarify a little bit?
What's the meaning of the CX?
Good. C is just some number, some scaling that you can put any number. 4, -15 is just saying if I have a number, like if I'm trying to do the integral of -13x from 0 to 5 dx, that just says the negative 13 comes along for the ride, the x increases in a power, and I divide through the power pattern. And then I use this structure where I plug in 0 and I plug in 5. So I do this structure of negative 13 something squared over 2. I plug in the 5, and then I take away the negative 13 something squared, plug in the 2.
So the x squared, where did that come from? Did that come from the 13x and the dx?
It came from the power pattern. There's a power pattern right here that is justifying it. Power pattern. Right? Because this again goes back to our exploration. I'm trying to find perfect area. How have we explored area in the class? Usually through Riemann sums. Unless there's just a very blatant geometric shape that we can play with, we've been doing it through Riemann sums. I don't want to do Riemann sums once I realize that all Riemann sums follow a pattern. I might as well just do that pattern. So this right here is me following the pattern that Riemann sums have without doing the Riemann sums directly, which is fine because it's going to result in the exact same thing and we've already justified it. So I'm following the power pattern. The power pattern says, take this structure, increase the power, divide by that new power. So that's what I did. And then I'm just using it in the same way that I would have used the answer that popped out of my Riemann sums.
Okay.
So it's a whole new thing. I'm not multiplying x times dx. I'm not plugging in dx. I'm not plugging in x. I'm not like this power pattern right here. This is us doing a pattern that would happen if we actually brute forced the Riemann sum. Because remember, the Riemann sum took us like 40 minutes, right? Like I think it took us like an entire class period for me to do one example, right?
Mm-hmm.
So like I don't want to do that once I find that there's a shortcut that means the same thing. In the same way that I don't want to add up I don't want to add up 100 threes with my calculator if I know that I could do a shortcut which is called multiplication, right?
Right.
So that's the idea. There's a shortcut we found that we can do these things in like 1 or 2 steps when we don't have to go through the brute force of rectangles anymore.
Okay.
Okay?
And
Well,
then-
let that one marinate a little bit. So Doug, to go back to your question, and then I saw that we had another visitor, Matthew. Hang tight, Matthew. So let's do an example of kind of where you're starting to see us going. To answer your question, yes, this power pattern only works for if I have x to a power, like times something, right?
Yeah.
Like that's the only time it ever works. Now, that being said, those come up in the real world quite often, right? Like the extra credits have all involved linears or quadratics. When you're talking about gravity and free fall and construction, those are all often quadratics or, you know, very close to multiplication afterwards style. Like it's all like, these are very prevalent structures in the real world. So it's okay that like what we have found only works for this massive category of examples. That's pretty cool. On the plus side though, we actually can generalize it a little bit more because take a look at this. If we do 0 to 5 of x squared plus 3x dx. We know behind the scenes that the logic supporting all of this is addition in rectangles, right?
Yes.
So if it's all just addition in rectangles and the sizes of those addition in rectangles, then this is saying I want to add up a bunch of rectangles that I formed through addition.
Yep.
Well, that's pretty clearly going to be the exact same thing as finding those rectangles and then adding them versus finding the addition and then making rectangles out of it. Like it's the exact same thing.
Okay. Yeah.
Like once we understand that this is all just adding in rectangles, then if it's adding in rectangles, let's just add in rectangles however we want to rectangles and add. Like it's all factoring in rectangles. So this really quickly becomes something that I can use for separating these problems Because again, this is just a bunch of addition of 3x's, right? Making rectangles on the way. So it makes sense that I can factor a 3 out because it's all just addition and rectangles.
Yep.
And then from here, how do I do this next step? Power pattern, right?
Yeah.
Now I've got something that matches the power pattern. So that goes up by 1, divides to compensate. I still need to plug in. That's fine. And this one over here becomes 3 up by 1 to squared, divided by 2 to offset. I still need to plug in. So this is going to become 5 cubed over 3 minus 0 cubed over 3 plus 3 times of 5 squared over 2 minus 0 squared over 2. Plug that in your calculator, and you've now done the area underneath this wonky curve.
Okay.
And it works for any combination of any of them. Make this 20, follows the same rule. Make this, negative 13, it follows the same rule. The number of different things you can do is bananas once we've got this captured and we understand where it comes from.
Okay. All right. No, that
Right? I mean, so now it's like, oh, all multiplication, all division is fair game because division's negative exponents, and we already do power rules. So like all division, all negatives, all multiplication, all addition, all subtraction, all of that's fine now.
okay.
Or now, like a couple of different things. If you did like integral from 0 to 5 underneath like a log function, okay, yeah, that's going to be something else. Like, we'll talk about that. We'll talk about that later when we're ready to start talking about variety problems. Like that's going to be something that doesn't work for the power rule because I don't have the conditions of the power rule. I don't have something with the power.
Okay.
But this is quite a bunch of different problems we can solve.
Okay. Nope. That's it.
Feel good?
Yes, I do.
So yeah, so the power pattern is not something that we just do because it works, although it is something that we kind of do because it works, but we proved why it works, and we have all of the same backing that we can then say, once I understand that it's all just a shortcut to getting me what I would have had with rectangles, run it.
Okay. Well, that works.